This lesson will cover the integration of frontend and backend in a D app. In a D app, the frontend and backend components work together seamlessly to provide a complete user experience. The frontend, typically built with technologies like React, is responsible for the visual interface and user interactions. It handles tasks such as fetching data, rendering UI components, and managing state. The backend, powered by Ethereum smart contracts, operates on the blockchain network. It handles the core business logic, data storage, and state transitions. The frontend communicates with the backend through the Web3.js library, an API, which provides a bridge between the user interface and the Ethereum blockchain. This separation of concerns allows DApp developers to focus on building intuitive and responsive user experiences while leveraging the security, transparency, and decentralization of the Ethereum network. Now we'll look at setting up the project. First, we create a React app with the command npx create-react-app dapp-frontend. Here we scaffold a new React project to serve as the front end. Then we install web3.js and add the library to interact with the Ethereum blockchain. Then we initialize the project to configure the project structure and set up the development environment. By following these initial setup steps, developers can establish a solid foundation for the DApp, laying the groundwork for integrating the front-end user interface with the back-end Ethereum smart contracts. To connect the front-end of your DApp to the Ethereum blockchain, you should use the powerful web3.js library. This JavaScript-based API provides a seamless bridge between your React application and the Ethereum network, enabling you to interact with the smart contracts and perform various blockchain operations. The code given above demonstrates how to initialize a Web3 instance and connect it to the Ethereum client. By using Web3.given or specifying a local Ethereum node URL, you can establish a reliable connection to the Ethereum network, allowing your front end to communicate with the backend smart contracts. First, we compile the contract. We use the truffle compile command to compile our Solidity smart contracts. This step ensures that the contract code is syntactically correct and ready for deployment. Then we deploy it to the blockchain. Once the contract is compiled, we use Truffle's migration function to deploy the contract to the Ethereum blockchain. This process involves interacting with the Ethereum node and securely transmitting the contract bytecode to the network. Then we verify the deployment. Then we verify that the contract has been successfully added to the blockchain by checking the transaction details and inspecting the contract state. To interact with the deployed smart contract, we'll need to import the contract's application binary interface and contract address. The ABI defines the contract application's programming interface, specifying the available functions and the parameter. The contract address is the unique identifier on the Ethereum blockchain where the compiled contract code is deployed. In this example, we'll first import the simple storage ABI from a JSON file containing the simple storage contracts ABI. Then we'll define the contract address variable with the address of your deployed simple storage contract. Then we'll create a new web3.eth.contract instance, passing in the ABI and contract address, which will serve as the bridge between your React application and the Ethereum blockchain, allowing us to call the contracts function and read its state. To build A robust decentralized app using Web3.js and React, we'll need to set up basic React components that can interact with the deployed smart contracts. This component will serve as the user interface, allowing users to interact with the contract's functionality directly from the front-end application. First, we use a single AMP component that imports the necessary dependencies, including the Web3 instance and the simple storage contract instance. Then defines two state variables, data and stored data, to manage the input value and the data retrieved from the contract. The handle set data and handle get data function allows users to update the contract state and fetch the stored data. MetaMask is a popular browser extension that allows users to manage their Ethereum accounts and connect to decentralized applications. The example given here helps us to enable the MetaMask extension and create a new Web3 instance connected to the user's Ethereum wallet. This seamless integration enables users to interact with your dApps smart contracts directly from their MetaMask-enabled browsers, enhancing the overall user experience and security of your application. To enable users to interact with your dApps built with Web3.js and React, it's very important that we properly handle their Ethereum accounts. The example here demonstrates how we can fetch and display the currently connected user account within your React component. By using the web3.eth.get accounts method, you can retrieve the list of available accounts and store the first one in the component state using the use state hook. This allows you to seamlessly display the connected account information to your users, ensuring that they are aware of which Ethereum wallet is being used to interact with your dApp. Update the state of a smart contract deployed on the Ethereum blockchain. You can leverage the power of Web3.js in your React-based decentralized application. This example shows how to send a transaction to the simple storage contract, modifying the stored data value. The handle set data function first retrieves the list of the available Ethereum accounts using the web3.eth.get accounts. It then calls the set data function of the simple storage contract instance, passing the new value stored in the data state variable. The send method is used to execute the transaction, specifying the from address as the first available account. This process updates the contract's state, effectively modifying the stored data on the Ethereum blockchain. To read the state of a smart contract deployed on the Ethereum blockchain, you should leverage the web3.js library in your React-based decentralized app. This code demonstrates how to call a function on the smart contract to retrieve the stored data. The handle getData function first awaits the execution of the getData function on the simple storage contract instance. This method call is made using the call function, which allows you to read the contract state without modifying it. The retrieved result is then stored in the component stored data state variable using the set stored data function. To provide feedback to the user about the transaction status, you can leverage the power of React State Management. In this code, the status state variable is used to track the correct transaction status. When the user initiates a transaction to update the contract state, the handle set data function first sets the status to transaction pending, informing the user that the transaction is being processed. After the transaction is successfully sent using the simple storage method, the status is updated to transaction complete, letting the users know that the operation has been successfully executed on the Ethereum blockchain. Displaying this transaction status in real time helps create a more responsive and user-friendly DApp experience. Implementing robust error handling is crucial when building DApps that interact with the Ethereum blockchain. This provided example demonstrates how to handle errors in the handle set data function, which updates the state of the simple storage smart contract. By wrapping the blockchain interaction in a try-catch block, you can catch any errors that may occur during the transaction and provide meaningful feedback to the user. When an error is encountered, the catch block logs the error message to the console, allowing developers to easily debug and troubleshoot their issues. This approach improves the overall user experience by preventing the DApp from crashing or displaying confusing error messages, and instead provide a clear and concise explanation of the problem. To ensure your DApp stays up to date with the latest data from smart contract, it's important to implement a mechanism to periodically fetch and update the user interface. The provided example demonstrates how to use set interval function in React's use effect hook to achieve this functionality. Within the use effect hook, an interval is set to execute a callback function every 5 seconds. This callback function uses the simple storage.methods.getData.call method to retrieve the latest data from the smart contract and updates the stored data state variable accordingly. The clear interval function is then returned to clean up the interval when the component is unmounted, preventing potential memory leaks. Optimizing gas usage for creating a DApp is a very important part. First, we can minimize the state changes to optimize gas usage. Reducing the number of state-changing transactions is crucial. By minimizing these updates to the smart contract state, you can significantly lower the overall gas costs incurred by your users, making your DApp more efficient and cost-effective. Then we can optimize the contract code. Carefully optimizing the code of our smart contracts can also help reduce gas consumption. This includes employing efficient algorithms, minimizing redundant computations, and leveraging gas-saving techniques like storage optimization and gas-efficient data structures. Then we can utilize efficient data structures and storage patterns in your smart contract, and by carefully designing the smart contract data model, we can minimize the amount of data that needs to be stored and accessed, leading to lower gas cost for your users. Here are some very good security practices. We can thoroughly validate and sanitize all user inputs to our DApp to prevent common web vulnerabilities like SQL injection and cross-site scripting attacks. We also can handle reentrancy attacks. Reentrancy vulnerabilities can allow malicious actors to repeatedly call contract function and drain funds. We can use the check effects interactions pattern to avoid reentrancy issues and ensure the security of our DApp smart contracts. We need to use secure libraries. We can leverage well-established and audited libraries and frameworks while building our DApp to benefit from their security features and best practices. This includes using secure versions of Web3.js, React, and any other third-party dependencies to minimize the risk of vulnerabilities. Now, to test the DApp, we can first write the unit tests. We first rigorously test our smart contract code to ensure its functionality and logic work as intended. Then we run integration tests for front-end backend. We validate the end-to-end integration between your DApp's front-end and the underlying Ethereum blockchain. We perform integration tests to confirm seamless data flow, transaction handling, and the overall coherence of our applications. Then we use the user acceptance testing. We engage end users to thoroughly test the DApp and provide feedback. Conduct UAT sessions to identify usability issues, improve the user experience, and ensure your DApp meets the target audience's expectations. Here is an example of the DApp deployment. The first step is to deploy DApp in the underlying smart contract to the Ethereum blockchain. This involves compiling the contract code, configuring deployment parameters, and executing the deployment transaction to make the contract accessible on the network. Then we will host the front end. With the smart contract deployed, the next step is to host the front end of your DApp on a web server. This could be a platform like GitHub Pages, Netlify, or any other hosting services that can serve your React-based application. Then we build and deploy. To deploy the DApp, we'll need to run the npm run build command to create an optimized production build of your React application. Once the build is complete, you can deploy the contents of the build folder to your web server, making the DApp accessible to users on the internet. So in this module, we figured out how to integrate front-end and back-end and using web3.js to make a DApp.